Okay, good evening, everybody. I will be giving you the first lecture on arches. I will give you 3 lectures on arches so that the subject is not that heavy. It is graduated on several, or it is divided into 3 lectures. This is the continuation of chapter 4. Chapter 4 is covering cables, and we studied that last time. And arches, this is the second topic. Let me first go into types of arches. The first type of arches, these are hinged arches. Hinged arches, whenever you are having an arch like this, the 2 supports are hinged, it can accept any kind of loading, either concentrated load, non-uniform loading, or maybe a couple, like that. The deformation of the arch will be like this due to the effect of the applied loads. You notice here that you are having angle theta that is not equal to 0, and you are having here angle that is not equal to 0. The reactions that we have will be vertical reaction and horizontal reaction. Unlike the cables, the horizontal reaction is pointing inward. Why? Because if you removed this support, the arch would like to move in the horizontal direction like this due to the effect of the applied loads. Now this support is prohibiting this movement, يبقى as if we are having a horizontal reaction that keeps this joint in position. According to this, whenever you are cutting a section in the arch, unlike any beam, for example, this is my section, like that, what will be the internal force? The internal forces here will be normal force compression. Notice that the normal force is perpendicular to the section. And there will be shear also, and there will be bending moment. يبقى in the hinged arches, we are going to have the 2 ends are hinged. There is rotation at the 2 ends. Whenever you are cutting a section, you will have basically normal force compression, and you will have shear and bending moment. Okay? This type of arches is statically indeterminate, because if we count together, how many reactions do we have? We have 1, 2, 3, and 4 reactions. We are having 3 equilibrium equations, no condition equations, يبقى therefore this is once statically indeterminate. The other type of arches, clamped or fixed arch. Instead of having hinged support, we are having fixed support though. Again, we can support distributed load, we can support concentrated load, or external moment M. What is the difference between this type of arch and this type of arch? There is no rotation here, because the fixed support will prohibit. So we are having theta is equal to 0, and we are having theta is equal to 0. Due to that, I will have vertical reaction, horizontal reaction, and moment reaction. And on the other side, also we are having 3 other reactions. This problem again is statically indeterminate, but it is 3 times statically indeterminate because we are having the number of equilibrium equations is 3, the number of unknown reactions is 6. So this means that the degree of indeterminacy is 3. Here, the equilibrium equations, they are 3, and the number of external support reactions is 4. Therefore, the degree of indeterminacy is 1. The other type of arches, these are 3 hinged arches. In this type, we are having the arch like this, but it is provided with an intermediate hinge. This one can also accept any kind of loading you wish. It can accept distributed load, concentrated load, or a couple. Again, the deformation will be something like that. Okay, here we are having theta. Theta is not 0, and theta is not 0. We are going to have 2 support reactions, R1 and R2, R3 and R4. Whenever we are cutting a section in the arch, we are going to have normal force, we are going to have shear, and we are going to have bending moment. The same thing here, the same thing here, the same thing there. When you are cutting a section in the arch, you are always getting 3 internal forces. But this problem is different from the clamped and the hinged arches in the fact that it is statically determinate, because the number of equilibrium equations is 3, the number of condition equations is 1, and the number of support reactions is 4. This means that the total number of equations is the total number of support reactions. Therefore, this is determinate. This means that I cannot study this in our course because we are only focused on determinate structures, and this one as well, but we can solve 3 hinged arches. So I'm going to explain for you 3 hinged arches. This curve might be a parabola, or it might be a part of a circle. So we are going to see how to solve for the internal forces in this type of arches. So simple, we are just directly applying the equilibrium equations. There is a 4th type of arches. Let me explain this as well. This is called funicular arches. Now, these arches are having so many shapes, but basically they must be hinged and, for example, subjected to distributed load like that. Now, the equation of the arch itself, if I want to describe the geometry of the arch, this is the x coordinate and this is the y coordinate. The funicular arch is such that when you are cutting a section here, again, we are having, as usual, R1 and R2 and R3 and R4. What's the difference between this one and between the 3 hinged arches or the hinged arches? When you are cutting a section like that, okay, you are having the reaction R2, the reaction R1, and the distributed load. The difference is that the geometry of the arch itself, or the equation of the arch itself, is suitable for this kind of loading such that when you calculate the internal forces, you will find that you have normal force compression as usual. This is not equal to 0. But when you calculate the shear, you will find that the shear is equal to 0. When you calculate the bending moment, you will find that the bending moment is 0. يبقى what's the difference? Whenever we are having a funicular arch, when you calculate the internal forces, you will find that you don't have except normal force. The shear is 0 and the bending moment is 0. يبقى this is the cheapest types of arches because you know that the bending moment is having the most severe effect on any cross section. When you are having bending moment or when you are having internal bending moment in the clamped or in the three hinged arches, in the general three hinged arches, you will have to design the cross section to afford or to stand the effect of the bending moment. This will let the section to be very large. If you want to make the arch optimum, the cheapest solution, then you have to select the shape of the arch so that it would be a funicular arch. Our lecture today will be focused on funicular arches. How can we select the shape of the arch to qualify as a funicular arch, and how can we compute the internal normal force compression? I don't have shear and I don't have bending moment. How can we compute the internal forces there so that this will qualify as a funicular arch, and if we want to design it, we know the internal force. Okay, let me start this part. Okay, so I will start with funicular arches. Let us remember what we took together in the first lecture of the cables. If we have, this is a cable like this. If we have a cable that is subjected to force P1 and P2, and here we are having sag H1 and we are having sag H2, and these distances L1, L2 and L3. Okay, and this support is A, B, C and D. Now, because this is a cable, it cannot support any internal moment, as we said before. So any point is considered as an intermediate hinge. So I can take moments about point D to determine the reaction AY. Sigma Fy is equal to 0. I should be able to determine the vertical reaction dy. Because this is a cable, we are having tension here. يبقى therefore the horizontal reaction should be outward like this. Every point qualifies as an intermediate hinge. يبقى therefore we can say that if we take sigma, the moments about point B from the left hand side, we can say that this is equal to 0 because I know that the internal moment here is 0. And let me take, this is the positive direction. So I have H times H1 minus AY multiplied by L1 is equal to 0. Very good. Also, this point qualifies as an intermediate hinge. So if I took the summation of moments from the right, so if I took here summation of moment of point C about the right hand side, we can claim that this is equal to 0. Let me take this as the positive direction. So H multiplied by H2 minus dy multiplied by L3 is equal to 0. Now, What if we come here and we reversed this upside down exactly? Okay? Here we are having H1, and here we are having H2, and we are having the load P1 and the load P2, and these distances L1 and L2 and L3. So I took the same geometry of the cable and reversed this like that. From the skew symmetry, if this is point A and this is point B, C, and D, we are having here vertical reaction AY, vertical reaction DY, and because of skew symmetry, imagine that this is no longer a cable, but it is something rigid. It is a rigid member like that. Due to the effect of the loads, this wants to open like this, therefore the effect of the horizontal reaction will be H, but inward, not outward. Okay? So now, in this situation, when it was a cable, it was supporting tension force. The force is getting out of the joint. But when we reversed the problem and we took the same geometry and the same loads exactly, the direction of the horizontal reaction is reversed. This horizontal reaction is outward, this horizontal reaction is inward. And what will happen? The member will develop normal force compression. So the internal force is towards the joint. Okay? طيب, let us examine something. If I want to get the moment about point B, what do? We are going to take either the left hand side or the right hand side. So I will say that the moment about point B is equal to. Now, the vertical reaction is causing positive moment because the tail of the arrow is under the datum. Therefore, I'm having AY multiplied by L1 minus. The horizontal reaction is rotating in the opposite direction. The tail of the arrow is above the datum. Therefore, this is minus H multiplied by H1. This looks familiar. If H1 is the same as H1, and if L1 is the same as L1, and AY is the same as AY, and H is the same as H but reversed in direction, what do you think this equation would be? If you look to this equation here, you will find that H1 minus AY L1 is equal to 0. We are having the same AY, the same L1, the same H capital, and the same H1 small. Therefore, this means that the moment at point B is equal to 0. طب استنى بقى. The moment here is equal to 0, and the moment here is equal to 0. I have nothing in between, also the bending moment here is equal to 0. All what I have is compression. And what is the magnitude of this compression? It is exactly like this tension. Instead of having tension with magnitude T1, I am having compression with magnitude C1 equal to it in magnitude but opposite in direction. طيب, what if you try to determine the moment at point C? You will say that the moment at point C equals. Either you will calculate this from the left hand side or the right hand side. The right hand side is easier. So I will take dy multiplied by L3 minus dy is rotating in this direction, so it is causing a positive moment, but the horizontal reaction H is rotating in this direction, so it is causing a negative moment. So this is minus H multiplied by H2, and you will find that this term is exactly like this term. The value of H is the same value of H, H2 is the same as H2, dy is dy, and L3 is L3. يبقى therefore this term is equal to 0. Okay? يبقى here I am having 0 moment and here I am having 0 moment. I have nothing applied in between. يبقى the moment also is equal to 0. Here I am having 0 moment and 0 moment. I have nothing applied in between. So I am having 0 moment. So what is the definition of a funicular arch? It is very clear. The funicular arch is having the same shape of a cable, but reversed. When you are reversing the cable like this, you will find that the external reaction will be reversed. The internal forces that will be developed, there will be compression instead of tension with the same magnitude of the tension. Okay? And we have 0 shear force and we are having 0 bending moment. So if I want to form a funicular arch, I would imagine how would the shape of the cable would be when it is subjected to this kind of gravity loads. And I will reverse this exactly in order to get a funicular arch. Okay? So we can solve the funicular arch by the concept that the internal moment anywhere is equal to 0. Or we can say that the shape of the funicular arch will be exactly the same shape of the cable, and we know the shape of the cable is identical to the shape of the bending moment of an equivalent beam. So we can work with all of these concepts. Now let us have an example to demonstrate this. How would we get a problem on funicular arches? Example, establish the shape of a funicular arch and then find the magnitude of compression in all members. We are having a problem like this. This distance here, it is 6 by 10 foot, 60. This height here is called the rise of the arch. If this is point A, B, C, D, E, F, and G. We are having loads applied, 24, 20, 20, 20, and 24. The rise of the arch in the middle is given 15 foot. We want to determine the value of H1 and the value of H2. So how can we solve this problem? It is required to determine this magnitude and this magnitude so that this will qualify as a funicular arch. Take care that this is a straight line and this is a straight line and this is a straight line like that. This is a straight line. Why? Because if you imagine that you are having a cable supporting these concentrated loads, then the cable would be straight between one load and another. The same thing will be for the funicular arch because it is taking the same shape of the cable. يبقى all what I need is to determine H1 and H2 so that this will qualify as a funicular arch. Of course, this value is H2 as well from symmetry, and this value is H2 as H1 from symmetry. From symmetry, the reaction here and the reaction here are equal and equal to the half the magnitude of the loads applied. This is 60 and 48, 108 over 2. So this is 54 and this is 54. So now I need to get the horizontal reaction and the horizontal reaction. We couldn't have solved the problem except by giving us the rise of the arch at a particular point. So I'm going to use this height here to determine the horizontal reaction H. So I will start solution. Now, I can say that the summation of moments about point B is equal to 0 because I want this to be a funicular arch. But when I do that, when I take the left-hand side, I will have two unknowns. I will have the horizontal reaction in addition to the rise that I want to get. I cannot take moments here, but I will have to take moments at point D where I know the magnitude of the rise of the arch. So I will say sigma, the moment about point D from the left-hand side, that is equal to 0. Now, this is the positive direction. I am having 54 multiplied by 30 minus 20 multiplied by 10, which is the moment caused by this force multiplied by 10, and the moment caused by this force multiplied by 20. And we will have to include the moment caused by the horizontal reaction. It is rotating in this direction like this. It is H multiplied by 15. That is equal to 0. From there we get the value of H, and if you did this, it will be 62.67. Kips. Type. Very good. So I solved for this one. This is 62.67. Now I want to get the rise at point B. So we can claim that the moment at point B from the left-hand side is equal to 0. Now I am having only one unknown, which is H1. So sigma, the moments about point B left, is equal to 0. How did I get this rule? However, I don't have an intermediate hinge because this is a funicular arch. The moment everywhere should be equal to 0. So I'm having here, this is the positive direction. So I'm having H multiplied by H1 minus 54 by 10 is equal to 0. Therefore, if you substituted the value of H by 62.67, you will get the value of H1 is 8.62 foot. Time. I want to get also the rise of the arch at point C. So I will take moments from the left-hand side. So I will say sigma, the moments about point C from the left, is equal to 0. Again, this is the positive direction. So I'm having H multiplied by H2 minus 54 multiplied by 20. Now I'm taking the moments about this point, and I will have to include the 24 times its distance, which is 10. So this is plus 24 by 10 is equal to 0. From there, the value of H2 will be equal to 13.4. Okay? Now, if this value is 8.62 and this height here is equal to 13.4, this qualifies as a funicular arch. But if you changed this one, instead of 8.62, you made it 9 foot. and this one instead of 13.42 it is 14 foot, for example. Again, this arch will not be a funicular arch. There is only one geometry that will satisfy the condition of being funicular arch, and we calculated this value and this value exactly. If any of these loads was changed, or if any of these rises was changed, then this is no longer a funicular arch. The funicular arch is funicular for only one particular load case. Type. If I want to get the compression that will develop here, what do I do? If I want to get the compression force, the funicular arch is exactly like the cable, right? What did we say in the cables? In the cables, we said that the tension force is equal to the horizontal reaction over cosine theta. The same rule applies in the arches. So I can say the compression force is equal to the horizontal reaction over cosine theta. I will have here compression directed towards the joint C1, and here I'm having compression C2, and here I'm having compression C3. We will have to calculate theta 1 and theta 2 and theta 3. Okay? So I'm having theta 1 is equal to tan inverse 8.62, which is the value of H1 over 10. We can get this. And theta 2 equals tan inverse. This height is 8.62 and this height is 13.42. Is 13.4. So the difference between them here, and we divide this by 10. This is 13.4 minus 8.62 over 10. I should be able to get theta 2. And theta 3 is tan inverse. Again, this is 13.4 and this is 15. The difference is 1.6. This is 15 minus 13.4 over 10. Therefore, finally we can say that C1 is equal to the value of H is 62.67 over cosine theta 1, and C2 is 62.67 over cosine theta 2, and C3 is 62.67 over cosine theta 3. Exactly the same forces, that the same tension force that would develop in the cable will also develop in the funicular arch, but instead of being tension, it will be compression. One student might ask me, this means that the funicular arches are always composed of straight line segments like this? No, not necessarily, according to the type of loading that we have. So let us have another problem. Example 2. Establish the shape of a funicular arch for the shown loading. Now, I am having here hinged arch that is subject to a uniform load W. Let us say that this span here is L over 2 and L over 2, and the height here is H. What do I want to get? If this is the y-axis, and this is the x-axis, I want to get the function of this curve. Is this curve linear so that it will satisfy that the moment everywhere is equal to 0? Or is it quadratic? Or is it cubic? Or is it with the fourth or of the fourth degree? We don't know. Let us calculate that. Of course, in the funicular arch, all the points are considered to be zero moment or intermediate hinges, so there is no problem that we can assume that we are having an intermediate hinge here. From equilibrium, this reaction would be W L over 2, and this reaction would be W L over 2. There will be a horizontal reaction H and another horizontal reaction H. How can we get the horizontal reaction in terms of the parameters given to us? We can take moments about point C, for example. So I will say the summation of moments about point C from the left is equal to 0. This is the positive direction. Then I am having H multiplied by H minus WL over 2 times L over 2. And this is plus. I will have to take the moment caused by the portion of the load left of C. This load here is W L over 2, and it is at a distance of L over 4. So this is minus or plus W L square over 8 is equal to 0. From there, the value of H will be W L square over 8H. So this is the magnitude of the horizontal reaction. Now I want to get an equation for this curve. So why don't we cut a section here like this and we take the left-hand side? Let me elaborate this here. So we are going to take, this is the y-axis, this is the x-axis, and this is point C. I am cutting a section like that. I am only taking this portion of the arch. I am cutting a section here like this, okay? We are having here reaction WL over 2, and we are having here horizontal reaction H. Since the origin is here, يبقى this is the y coordinate. يبقى this means the remaining part should be L over 2 minus y, because this distance is L over 2. يبقى if you are taking this as the y coordinate, يبقى the remaining should be y this is L over 2 minus y. Sorry, my x. This is x. This is x because it is parallel to the x direction. And also, the coordinate of this point is y, and we know that this height or the rise of the arch is h. يبقى therefore the remaining part is h minus y. Very good. يبقى I'm taking a segment, the right hand side, the reaction is WL over 2, the horizontal reaction, we know its value is WL square over 8h, and we know the height from this point to this point is h minus y, and the horizontal distance from this point to this point is L over 2 minus x. What kind of forces do we have here? Because this is an arch, we should have compression, normal force, we should have shear. Now the cut section is on my left hand side, يبقى the positive shear will be upward like this, and we should have bending moment. The tail of the arrow is under the datum, assumed to be positive, the moment is positive and the shear is positive. If this is point O, now I want to get the magnitude of the bending moment. What do I say? يبقى the moment at point O is equal to W L over 2 times its distance, which is L over 2 minus X. Okay? And we are having here, this is minus H multiplied by H minus Y. I'm taking moments above this point and I'm adding everything together. Okay? And I will take the resultant of this loading, which is W, multiplied by the distance L over 2 minus X, times half of this distance to get the moment. يبقى this is minus W multiplied by L over 2 minus X multiplied by L over 2 minus X over 2. This would be the internal moment. طيب, if I want to determine, or if I want to let this arch to be a funicular arch, the internal moment should be equal to 0 anywhere, because I am cutting at an arbitrary section. I want to select the shape such that the internal moment anywhere is equal to 0, and this is an arbitrary point at a distance x from the origin and a distance y from the origin. Okay, so let us call, or let us set this moment is equal to 0. From there I will get a relation between x and y. يبقى therefore I am getting the shape or the equation of the arch itself. يبقى from there y is equal to, if you did this, of course you can cancel out the w's together and you can substitute here the magnitude of h is equal to w L square over 8 multiplied by h. Okay, this you can substitute by its value. يبقى you can finally prove that the value of y is equal to 4h over L square multiplied by x square. What did you conclude? H is a constant number and L is a constant number. We were given the rise h small and we were given the span L. So this is some constant. يبقى this means that we are having y is some constant, because this does not change, multiplied by x square. يبقى what does this mean? It means that for this arch to qualify as a funicular arch, this curve must be a parabola. It should be of the second degree. طيب, if this is cubic, يعني instead of x square you made x cube, the moment m naught will no longer be equal to 0. Okay? طب if this is straight, يعني this means that y is equal to some constant multiplied by x to the power of 1 linear. يبقى again this is no longer funicular and you will have internal bending moment. يبقى the only case that this would be a funicular arch, يبقى the arch would be a parabolic arch. If you imagine that you are having the origin at the center, يبقى therefore the equation here would be y is equal to some constant multiplied by x square, and we prove together that this constant is 4h over L square. Therefore, if I'm having a distributed load and I want to establish the shape of a funicular arch, this is the optimum, cheapest type of arches, I would select the shape of the arch to be a parabola. Okay? Now let us go further a little bit in this problem. If I want to determine the normal force, يبقى now we proved together that to be a funicular arch, that y is equal to 4h over L square multiplied by x square. Okay? Now, what if I want to determine خلاص بقى the moment is equal to 0, there is no moment, the shear is also equal to 0, and all what I have is the normal force. Of course, the normal force should be compression, and it should be directed towards the section like this. If this angle is theta, and if I want to determine the normal force, how can I get the normal force? Very easy, I can say sigma fx is equal to 0. The only force that I have is h. مش كده؟ يبقى therefore if I said sigma fx is equal to 0 and I'm having this is the positive direction, يبقى therefore n cosine theta, because you are getting the horizontal component of n, the only horizontal force that will balance with it is h, is equal to h. يبقى therefore n is equal to h over cosine theta. That's what we used in the previous example exactly. But this is not an answer. I want to get the value of n in terms of the geometry of the problem, the horizontal reaction, in terms of the rise instead of in terms of the span, in terms of the load. This is not considered to be a final answer for me. Okay, now if we take, we all know that this is a parabola. It is not a straight line. Okay, if we take a very little segment like that, this is dy and this is dx. Because this distance is very small and this distance is very small, we can claim that this is also linear. يبقى this angle here is theta. Okay? يبقى in this triangle, if we elaborate, this is dx and this is dy and this is theta. We can say that tan theta is equal to dy by dx. Okay. طيب, but what is y? Y is equal to 4h over L square multiplied by x square. يبقى if I want to derive this in terms of x, it will be 8h, مش كده؟ 8h multiplied by x over L square. يبقى therefore, what do I know about the tan? Again, why am I doing this? I don't want to give you the result as normal force is equal to h over cosine theta. Cosine theta is not a solution. I want to remove the value of cosine theta and put something that is known in the question. Okay? So I'm doing some sort of mathematical derivation so that I can remove this cosine theta and put something else. Now we determined that tan theta is equal to dy by dx from calculus, we know that. And because we know the equation of y is equal to 4h over L square x square, we derived this once with respect to x and we got 8h x over L square. What do you know about the tan? If you are having, this is theta, tan theta is the opposite over the adjacent. يبقى as if the opposite is 8h x over L square and the adjacent is 1. يبقى فعلا tan theta is equal to the opposite over the adjacent. It will give me the same number that we have here. يبقى therefore, what would be the hypotenuse? It is root 1 square plus 8h x over L square whole square. يبقى if I want to get cosine theta is the adjacent over the hypotenuse. يبقى therefore cosine theta is equal to 1 over root 1 plus 8h x over L square whole square. يبقى from there we can say that the normal force, to get a general solution بقى, the normal force is equal to h over cosine theta. Please substitute the value of cosine theta, which is h root 1 plus 8h x over L square whole square. But we prove together that h is equal to WL square. So this is equal to the value of n is equal to WL square over 8h root 1 plus 8hx over L square whole square. This is the magnitude of the normal force. يبقى according to the value of x, you can determine the normal force. You will find that if we plotted here the normal force value, this is x and this is y and this is our arch. Okay, here we are having this distance is L over 2 and this distance is h. Question: if you want to get the normal force at this point, what would you do? You are going to substitute at this point. This is the origin. The coordinates here is 0 and 0. So we are going to substitute here by 0. يبقى this will be root 1. يبقى this value is WL square over 8h. يبقى this is here the normal force is WL square over 8h. And it will have, of course, it is compression, so it is drawn under the data. Now, if you want to substitute, if you want to get the value of the normal force at this point, you will substitute the value of L of x is equal to L over 2. So if you did this, you will get the magnitude of the normal force here is bigger, and it will be equal to W L square over 8h multiplied by root 1 plus h square L square. And the magnitude of the normal force is changing gradually in the middle like this. What do we learn? We learn that the compression force is increasing gradually from the middle up till the support, and at the support we are having the maximum value of the normal force. Because the normal force always in the arches is considered to be compression, you will find in the book and in your example sometimes this is called thrust. The meaning of thrust is exactly normal force, but it is subject to compression. Of course, don't worry about this problem. This was just illustrative. But if you have a funicular arch, probably 99%, I will give you a funicular arch that is subject to concentrated loads. So you don't have to go through that much of mathematical calculation. Okay? In the next lecture, I will be explaining for you 3 hinged arches. Now we finished the funicular arch. The funicular arch, all what we need from that is to determine the geometry of the arch, the magnitude of the rise of the arch, and the magnitude of the normal force or the thrust. And this is equal to h over cosine theta. And we did some simplification here if we are having distributed load. The other types of arches that we can solve together in this course is the 3 hinged arches. The 3 hinged arches, you will have to calculate the normal force, the shear force, and the bending moment because it is no longer funicular, and we will use the principles of superposition or the principles of equilibrium that we learned together throughout the course. There is nothing new about that. So I will give you the other lecture will be on 3 hinged parabolic arches. Okay, thank you.